presentation, and later on I will share the link in our WhatsApp group. Okay. Hi, hello everyone. Alright, before we start, let me introduce myself. You guys can call me Dr. Rose or Madam Rose. Okay, I will be your tutor for this semester. We will start by this May and end by middle of August, if I'm not mistaken lah. Alright. So today we are here for our first tutorial on digital circuit design. Okay, the code is TEE 203. And for those who haven't joined the WhatsApp group, please text to my number. I have put, okay, let me pin the chat. Where is the chat? Okay, I've pinned here my contact number 0.9 019 950 3432. Okay, I've noticed some familiar names. Before this, there is few students enrolled in my previous class. Rajeswari, Khairil Azwan pun my student from previous class kan? Previous semester.
Yes, yes. The last two
Okay,
semester.
subjek apa?
That one.
Subjek apa ya?
Electronic and digital circuit, I think.
Electronic, analog electronic ke?
Analog electronic. Sorry.
Analog electronic, okay. So pusing-pusing kan kita jumpa orang yang sama je. Okay, that's good lah because you already know me, dah kenal saya, dah tahu saya cara saya conduct class and the whole semester macam mana kan, it will be easier for you lah, hopefully. Okay, but for those who this is the first time with me, okay, nice to meet you guys, and hopefully we will doing well for this throughout the semester. Okay, not to worry because we will try to help each other. Okay, saya tolong you, you tolong I. Okay, and kita make things easier for everyone lah. Okay, so actually for this subject, digital circuit design. Okay, let me give some brief overview on this course. Some synopsis lah. Okay, actually for this digital circuit design, it is the preliminary course that you need to have before you enroll for this digital circuit design is digital electronics. Okay, I believe that all of you already took the subject digital electronics before this. Okay, and okay, for this, before this, previous years, we have digital electronics with 5 tutorial, meaning that 5 chapter that we have to cover. Okay, I think around 2 years back, macam tu, we have digital electronics only. But now, we divide the digital electronics into 2 major subjects, 2 major courses, which are the digital electronics itself with 3 credit hours. Okay, previously we have 5 credit hours. That is why we have 5 tutorial. Okay, now we have 3 credit hours for digital electronics. Okay, and also we have digital circuit design, meaning that previously we have digital electronics 5 credit hours. Now we divide into 2 subjects, digital electronic 3 credit hours with and also the digital circuit design. Okay, so preliminary is the digital electronics 3 credit hours for you guys. Alright. Okay, for this subject, we are going to have 3 units. Okay, the first one is on the digital counter and shift counters. Alright, and the second is memories and programmable logic, and the third one is integrated circuit logic families. Okay. For digital counters and shift registers, okay, it is the expanse from the Boolean algebra that we have studied in digital electronics. Okay, Boolean algebra. I hope you guys still remember on that minimization of the bits, 1 and 0 bits that we have, and all the logic gates that we have in digital electronics. Okay, it is actually a concept of mathematics which we allows to manipulate the logic 1 and 0 bits of the binary system and manipulate of the Boolean function. Okay. And for second unit is on digital counters and for the second unit is on the memories and programmable. We study on the type of semiconductor memory that we have, and we will cover on the non-volatile memories and also the volatile memories. Okay, and also we discuss on the programmable logic device. It is on unit 2. Okay, for unit 3 it is on the integrated circuit logic, okay, families, and we cover on the digital integrated circuit logic and the bipolar transistor logic. Okay, also the unipolar transistor logic and the advanced integrated circuit logic. Okay, so that is the 3 major unit that we will cover on the digital circuit design. Okay, for this semester, okay, for the digital circuit design code TE 203, we will have 2 course assessment, okay, which are CA2 and CA1 and CA2. Okay. I'm not sure when is the deadline for both of the course assessment. Later on, I will ask the CC. Our CC is Dr. Hazri. Okay, if you guys have any issue on the submission of the course assessment, then you may apply via the system. Later on, Dr. Hazri will approve. Okay, must get approval from Dr. Hazri. Kalau tak ada lagi deadline for the course assessment, nanti I will ask Dr. Hazri. And for the course assessment question, then you may get from the FlexLearn. I believe that it is already in the FlexLearn. Okay. And for this semester, we only have the course assessment. Okay. For this subject, we are not going to have online lab simulation. Okay. Tak ada lab for this subject. So it is solely on the tutorial, okay, and throughout through the end of the semester, we might be have the final examination like previous semester. Every subject has final examination. Okay, it is online final examination. Okay, and that's for the course overview. Okay. Okay, so this is all the students that we have in these subjects, 9 students. Okay, can you guys see my screen? Boleh nampak my screen?
Can, Miss.
Alright, thank you. Okay. For unit 1, we have 4 subtopics to be covered. Okay, we will cover today 4 subtopics. Okay, my contact number is 019-950-3432. If you guys have any questions regarding the lecture and the notes, then you may ask in the WhatsApp group or you may text to my number personally. Okay, my contact hours is 24/7. Okay, you may contact me tak kira masa, but then tak kira lah tengah malam ke, if it is midnight. Let's say you are doing revision and then you have any question, then you may straight away text to my number, but then give me some grace period to reply. Okay, because during weekdays, I will be teaching at universities. So sometimes I might be in the middle of class. Maybe I tengah mengajar ataupun I tengah ada meeting. So that is why I can't straight away respond to your question. Okay, but then once I have the chance to reply, and then I will respond to you guys. Okay. Same goes if you have any questions nak tanya regarding the course assessment pun boleh. Okay. Alright. So we will go to our syllabus that we need to cover for today. Okay, digital counters and shift registers. Okay, we will see how to construct the counters, which are used as timers in many electrical devices. Okay, another important group of devices called the registers are also constructed from the flip-flop. Okay, registers are be it storage or the memory devices. Okay, we will get an inkling of how the memory works in the digital system. First, we go for the flip-flop. Okay. Okay, the term flip-flops in digital circuit refers to a type of circuit element, okay, that is commonly used as a building block for memory and sequential logic circuit. Okay, it is a vestible device that we can store one bit of information and can trigger the change state based on certain input signals. Okay, the flip-flop comprises of gates. Okay, kita tengok sekejap lagi. And flip-flop are essential component in digital circuit design as they are used to implement a wide range of digital systems, such as we use in counters, registers, and shift registers. Okay, they are also used to synchronize signals in the digital systems, which is important for ensuring reliable operation. Okay, basic flip-flop has two outputs we label as Q and Q bar. Q is the normal and Q bar is the inverted. Okay, we will see. Okay, here we have now we have basic set and reset flip-flop. Okay, set RS is reset and set flip-flop with output Q and Q bar. Okay, Q is the normal one, Q bar is the inverted. Okay. Okay, when a flip-flop is toggled by a pass, then it can retain, or we can say it can remember the input. Okay, it stays even after the pass cases. Okay, so for a flip-flop, it has memory characteristic. Okay, we can construct a truth table from these logic gates. Okay, logic gates here, it has two NAND gate. Okay, so NAND gate here. Okay, this is a truth table of the NAND RS flip-flop with input, set and reset, and output of Q and Q bar. This is actually Q bar. Okay. In the truth table, set and reset represent the input. S is set, R is reset. Okay. Q and Q, this is Q bar, represent the output. Okay, the first row truth table shows the case where both R and S input are low. Okay, this is both are low. This is one low and one high. Okay, second and third, and the fourth is both are high. Okay, this is the explanation here. Okay, the fourth row shows the case where both set and reset are high, and then this input combination is not allowed in the NAND RS flip-flop. Okay, that is why we have invalid output. Alright. Okay, for the first row, okay, the output will remain from the previous state. Okay, dia sama dengan previous state. Okay, and for the second and third, okay, it will convert. Okay, the second, okay, the causes of Q to be low and complement Q bar, it become high. Okay, the third one is high, and this is here is low. Okay, overall we have the truth table of the NAND RS flip-flop shows how the output of the flip-flop change based on the input applied to it, and provide a basis of designing and analyzing digital circuit that we use in flip-flop. Have the clock RS flip-flop. Okay, it has two input, the clock signal and the RS input. Okay, this is the clock signal, and this is R for S, and this is R input. Okay, it has a combination of 4 NAND gate. Okay, U1, U2, U3, and U4. Okay, the output of Q is synchronized with the clock signal and changes state only on the rising and falling edge of the clock. Okay, sekejap lagi kita tengok. Okay, and clock RS flip-flop are widely used in digital circuit, particularly in application where the synchronization and timing are critical. That is why, because it is synchronized with the clock signal. Okay, so this is the input of set and reset as the separated signal. This is clock and set, reset, and this is the output. Okay, and we get the truth table over here. Okay, we can use in this clock RS flip-flop used in wide range of systems such as in counters, shift registers, and memory elements. Okay, and they are essential for ensuring reliable and predictable operation of the digital circuit. Okay, next we have the clock JK. Okay, for clock JK, the input is slightly different here. Now we have input like this one here, called RS kat sini, and for clock JK it will be different here. Also, we consist of 4 NAND gate. Okay, for clock RS, it has two basic parts. Okay, the master section and the slave section. Okay, input J and K used to set as the set and reset of the output. Okay, the difference between RS and JK is the way we store and manipulate the data. Meaning that over here lah. Okay, and this is the construction of the logic gates. Okay, the difference between the RS and the clock JK. This is the truth table. Clock JK is more versatile and flexible than RS. Okay, RS is simpler and more straightforward. Okay, we can see here this is the truth table for clock JK flip-flop. Okay, and this is the clock input and setting here, and this is K is as reset. Q is the output and Q bar is complement of the output. Okay, as you can see, if we have the input J and K 0 and 0, okay, there will be no change at the output. Okay, and clock is high. If the clock is high, if we have input 1 for the JK, and the output will be toggled from the original Q output. Alright, next one we have clock D flip-flop. Okay, this is a D flip-flop with one input here, D, and input clock signal. Okay, input clock, and with the single output. Okay, the data of D flip-flop, okay, we call it as the delay flip-flop. Okay, for D. Okay, the type of digital circuit that store a single bit of data and use clock signal to synchronize input and output operation. Okay, for this data or delay flip-flop, okay, widely used in microprocessors, okay, also in memory devices and in communication circuit. Okay, That's why we have D flip-flop, okay, T flip-flop, or this toggle. Okay, the toggle flip-flop switches the Q output on each clock edge. Okay. The digital circuit that toggles the output between two states, okay, based on a clock signal. As you can see, we change from one state to another. Okay, it is types of single input and single output. Okay, this is a timing diagram, okay, for the T flip-flop here. Okay, input and the output. Okay, the T flip-flop commonly used in digital circuit for frequency division and also for the waveform generation and for state machine design. Okay, we can cascade this T flip-flop, okay, to form the cascade more than one T flip-flop together and form a larger counter. Okay, and we can allowing for more complex timing and the sequencing operations. Okay, that is types of flip-flop that we normally use in digital circuit design. Okay, next we go for the digital counters. Okay, digital counters are electronic circuit that count the number of input pulses they receive and display the count on a numeric display or output it to a computer and other devices. Okay, two basic types of digital counters is we have a synchronous digital counter and synchronous digital counter. Okay, for digital counter, we can use in wide range of applications, including the event counting, frequency measurement, and in control system. Okay, and we use digital circuits to create more complex system. Okay, such as if we want to create timers, what else? Sequences and digital circuit processors. Okay, we can say it is a counting device. Okay, for other common applications using counter is the up and down flow indicator, okay, in this, okay, the digitized temperature sensor and also used in the air conditioner system. What else? Also we can use in security system, automatic control system, and mostly we use in robotics and other applications where accurate timing is important. For digital counters, there are series of flip-flop to create a binary count sequence. This is for ripple counter. Okay. For each of flip-flop in counter divides the frequency of input signal by 2, okay, resulting to a sequence of counts that represent a binary number. Okay. For ripple counters, sometimes we also call as asynchronous counter. Item falls into another item repetitively. Okay, here we have 3 ripple counter. Okay, from JK flop. Okay, the
sorry, ma'am.
Yes.
Your voice is breaking.
Yes.
Your voice is breaking right now. Dia macam sangkut-sangkut. Your voice.
Oh. Is it? Sekejap lagi I join. Hi, boleh? Or still not clear?
Okay lah sikit. Clear.
Okay. Might be something wrong with my line internet kat sini. Okay, if not clear lagi nanti please inform ya. Okay, we will continue. Okay, we will continue with the ripple counter. Okay. Also we call as the asynchronous counter. Okay. Each flip-flop here we have 3 bit ripple counter with a 3 JK flip-flop. Okay, each flip-flop in the counter divides the frequency of input signal by 2, resulting to a sequence of counts that represent a binary number. Okay, the advantage here is for ripple counter, it is simple and inexpensive. Okay, however, because we need fewer components than as we compare with the another one of digital counters, which is the asynchronous counter. Sorry, it is a synchronous counter. Okay. However, for this type of counter, suffer from glitches and can be slow for high frequency input for the operation. Okay. In addition, this asynchronous counter, okay, the delay between output and the flip-flop and also the input of the next counter, okay, can cause the error in the count sequence. Let's say from one flip-flop to the another. Okay, as you can see, okay, this output for this flip-flop, okay, it will become the input for the next one. Same goes for the next one. Okay, meaning from stage by stage. Okay. It will encounter error from one to another. Okay, so next one we have synchronous counter. Okay, same goes here. Also, we form from 3 JK flip-flop. Okay, as you can see the combination. Okay, the connection, there is no connection here. Now we have connection from input to each one of the flip-flop. Okay, synchronous counter are a fundamental building block in many digital systems, and we can use in wide range of applications where it is for output, it is more accurate and reliable counting. Okay, if we need accurate and reliable counting. Okay, for complex, it is more complex but has advantages. Okay, one of that, it is more reliable. Okay, it is not susceptible to glitches, and there is no error in the count sequence. Okay. Okay, another difference also here, there is no AND gate here. Kat sini we have at another AND gate here. Okay, this is for synchronous counter. Commonly for the synchronous counter, we use in application that require high-speed counting, such as for digital signal processing, communications, and the data acquisition. Okay, here we have MOD8 down counter design. Okay, we have AND gate here, connect by output of Q bar here. Okay. Synchronous counter we can design as either up or down counter depending on the application. Okay, for an up counter, the count sequence starts at 0 and increases by 1 of each clock pulse. Okay, for down counter, the down counter starts at the predetermined value and decreases by 1 of each clock pulse. Okay, that's the difference between up and down counter. Okay, this is a 4-bit synchronous up counter. Just now it is 3-bit down counter. Okay, this is a 4-bit. Okay, 1, 2, 3. Each flip-flop for each bit. Okay. Okay, for this flip-flop, this one toggles on every clock pulse. Okay, the second toggles only if Q0 is high. And for the third one, we have sama juga kat sini, we have one AND gate, and now we have two AND gate, okay, between the third stage and the fourth. Okay, this is for the flip-flop toggles only if Q0 and Q1 are high. And finally, this one toggles only if Q0, Q1 and Q2 are high. Okay, this is the meaning that it will compare. Okay, compare the output here. Right, this is for 4-bit synchronous up counter. And this one here is also 4-bit, but it is down counter. What's the difference? Okay, kalau up, it has the AND logic gates here. Kalau down, dia ada kat sini. Actually for this one, this down counter, it connect from Q bar. Okay, if up, it connect from Q. Okay, let's see, down, connect from Q bar ni kan. Dia ambil dari Q bar. Okay, meaning that this one, we can also put this kat bawah sini. Okay, kalau kita letak kat sini. Sama. Dia ambil dari mana dia punya input. Okay, bawa up, dia ambil dari Q, previous flip-flop. Okay, if down, it takes the input from Q bar. Okay, that's the difference lah from up counter and down counter. Okay. Okay, that's for the counter. Next, we go for the shift registers. Okay, if boleh saya tahu tak, sekarang ni you guys in semester berapa? Is it 5 or semester berapa you guys?
Saya dah 10.
Sorry, semester 10?
Ya.
Kalau semester 10, meaning that dia lain sikit you guys punya calculation, WU punya calculation semester kan? Maksudnya subjek tu subjek dalam tahun ketiga ke?
Iya kot. Saya dah 10 lah.
Sebab one semester you guys ambil subjek 3 subjek je per semester. Maksimum berapa?
Maksimum 3, tapi saya selalu ambil 2 je.
Oh, that is why lah your semester dia lebih panjang because you guys is part-time student kan? Consider as part-time lah. Kalau I think kalau digital ni, kalau untuk universities awam, because I'm teaching at University Awam, Mara Universities, subjek ini I think dalam tahun ketiga lah. Okay, semester 6, I think semester 5 or 6 macam tu lah, lebih kurang ya. It is more than half lah. Kalau tahun kedua tu it is macam baru half of all the subjects kan. I think for this digital circuit design it is macam dah masuk tahun ketiga lah. Okay, so it's actually for this digital circuit design, okay, the fundamental concept you will use apply nanti di dalam subjek microprocessor or micro P. I believe that Wawasan also has a microprocessor subject. Okay, sebab microprocessor is also this is macam now is the critical ataupun crucial part lah juga in electrical engineering. Okay, it's more on applications lah. Okay, same for this shift register. Akan guna banyak sikit in microprocessors. Okay, because previous semester dekat my university saya ajar subjek microprocessor. Tapi kita more apply in what we call dia punya coding lah. Ada banyak programming. Okay, but the basic fundamentals datang daripada for this digital electronics and digital circuit design. Okay, that is good for you guys untuk faham this subject lah. Alright. Okay, next one we go for shift register. Okay, shift register it is a digital circuit that we can store and shift a sequence of bits. Okay, it is a type of sequence logic circuit that is commonly used in digital electronic. Okay, it consists of series of flip-flops, such as we can store 1 bit of the data. Okay, for the flip-flop, we can connect in change. Like previously, kita tengok it is connect in a series kan, with the output of one flip-flop connected to the input to the next output flip-flop first. Dia jadi input to the next flip-flop. Okay, it is concept dia lah connection in change or series. Okay. Describe the operation. We have SISO, single input, single output. SIPO, single input, or we have a multiple output. Okay. Sorry. Series input with parallel. It is either in series or in parallel. Okay, let's see first one. Is SISO and SIPO shift register. Okay, we can put it in series and also in parallel. Okay, as you can see here, we have 5 bit. Why? Because we have 5 D flip-flop. Okay, kenapa D? Because we can see kat sini it is, input is D. Okay, why 5? 1 flip-flop, remember 1 flip-flop, it is represent 1 bit. Okay, so now we have 5 bits lah. Okay. It is SISO ke SIPO. Okay, SISO it is series input and series output, serial in, serial out. Okay, for SISO. SIPO is serial in, parallel out. Okay. Apa lagi kita ada tadi? SIPO, PIPO, parallel in, parallel out, and PISO, parallel in, serial out. Okay. S series, P parallel. Okay, the first one is SIPO and SISO. The shift register we can operate in several different modes depending on how the data is we shift. Okay, the most common mode that is serial in, parallel out, SIPO. Okay, and we have SISO. SISO is serial in, serial out, and we have parallel in, serial out, PISO, and parallel in, parallel out, PIPO. Later on kita akan tengok dia punya connection, okay, satu-satu. Okay, now we have D flip-flop with SISO. Okay, serial in, serial out. Okay, the shifted out serially 1 bit at a time. Okay, 1 bit at a time. Next, kita tengok this one is SIPO. Okay, serial in, parallel out. Okay, input dia in series, output is in parallel. Kenapa? Because the output dia kat sini. Dia ambil from 1, 2, 3, 4 and 5. Meaning that it is in parallel. If it is in series, dia ambil straight macam ni. Okay, it is in series. This one is in parallel. Okay, in SIPO, serial in, parallel out mode, data is entered serially 1 bit at a time and then shifted out in parallel at all time. At all time meaning that it's simultaneously parallel out. Okay. For SISO, this one is SISO, serial in, serial out. Data is entered serially. The in is serially and shifted out serially 1 bit at a time. Output dia pun macam ni juga, in serial. Okay, that's the difference lah. Output in serial and output in parallel. Next one is parallel input and parallel output. Okay, this one parallel input and parallel output. Combination dia like this one here. Okay, it has 4 bit. Okay, 4 bit. If it is 5 bit, then tambah je lah lagi another D flip-flop. Okay. In parallel in, parallel out mode, data is entered in parallel and shifted out in parallel all at one time. Okay. Tengok dia punya output dia from each of the bit, each of the flip-flop dia. Okay. Next one, kita tengok parallel in, series out. Okay, this is parallel in, series out, 4 bit, also 4 bit, PISO. Okay. connection using 4 flip-flop for 4 bit. Okay, in parallel in series out mode, data is entered in parallel. It is entered one by one. Maksudnya, step 1 dia tak connect with previous one. Okay, and then shifted out serially 1 bit at a time. Okay, dia masuk from output, dia masuk to the next one. This one, output masuk to the next. Okay, inject to the next flip-flop. Okay. For the shift register have a wide range of applications, including in digital communication system, data storage devices, and in various types of digital signal processing applications. Okay, they are particularly useful for creating delays and also for performing various types of signal processing operation. Okay, next one, we have ring counter and Johnson counter. I think ring counter, Johnson counter ni ada soalan in course assessment. Saya tengok sekali imbas je. Okay, for ring counter and Johnson counter are two specific types of shift register which have unique characteristic and application. Okay, a ring counter is a type of shift register that is designed to generate a sequence of digital signal that repeat periodically. Okay, it consists series of flip-flop connected in circular fashion with the output of the flip-flop connected to the input to the next. Okay, circular fashion dia because this different kat sini lah. From output dia jadi input balik. Okay, output for the, let's say this is 6 bit kan. 6 bit to the 6th one dia inject to the first one. Okay. When the input signal is applied and then the data circulates through the flip-flop in a loop. Okay, this one lah, in a loop. Okay, the output of each flip-flop represents 1 bit of the counter and the pattern repeats after the final flip-flop kat sini. Alright. It will look back at the output queue, look back into the system. The ring counter have a variety of applications including in digital clocks, frequency devices, and in controlling the sequence of events in digital system. Okay, this is for ring counter. Ring counter, the output, okay, we take from the queue. Okay, let's see for Johnson counter. What's the difference? Can you guys see what's the difference between ring counter and Johnson counter? Okay, this is also 6 bit and this one also 6 bit. Okay, with the flip-flop. Okay, but then for Johnson, the output we take from Q bar. Also, we inject into the first A lah, the first flip-flop. Okay, here. Okay. Johnson counter, also known as twisted ring counter. Why? Because we twist here lah. Okay, the difference kat sini. Okay, it is a type of shift register that has a unique counter sequence. Okay, it consists of a series of flip-flop connecting in circular fashion with a output of each flip-flop connected to a logic gate generates the input for the next output. Dia jadi input for the next like here lah kat sini ya. Okay, the sequence of output of the counter generate a twisted pattern. Okay, with in which each bit in the sequence is the complement of the previous bit. This one lah. Okay, for example, the sequence for 4 bit counter would be 0001, 0011 and so on lah. Okay, Johnson counter are useful in digital system that require a non-repeating counting sequence. Okay, such as in frequency hopping, spectrum system, okay, and also in pseudo-random number and generator and the other crystallography applications. Also, we can use in sequence generator for digital signal processing applications. Okay, that's for ring and Johnson counter. Okay, previously we have asynchronous counter or ripple circuit. Okay, now we go for synchronous circuit design. Okay, it is more complex as compared to the previous one lah. Okay, the concept of flip-flop excitation table and state machine are introduced. Okay, synchronous circuit design are electronic circuit that are designed to operate in synchronization with a clock signal. Okay, in a synchronous circuit, all the circuit elements such as we have flip-flops, registers and logic gates are designed to operate only when the clock signal is in active mode. Okay. The synchronous circuit are widely used in digital systems such as in microprocessors, okay, digital signal processors, and in memory devices, okay, where the timing we need to be precise and critical for reliable operation. Okay, the use of synchronous design techniques help to reduce the timing uncertainties and improve the performance, also the reliability of the digital systems. Okay, this is the excitation table by using the JK flip-flop. Okay. The JK flip-flop is similar to RS, set and reset flip-flop, but there is no change in state when the JK inputs are both low. Okay, nanti boleh tengok balik dia punya truth table between JK and S. Okay. Okay, this the current value and the next value. Current value is the QT, let's say QT, and next value is Q at T plus 1. Okay, for the next state. Okay, the excitation table has the minimum input which will excite or trigger the flip-flop to go from its present state to the next one. Okay, this is the for input low, 0, 0, 0, and this is for input high. Okay, for the next value it will trigger or the toggle one. Alright. Okay, this is the truth table for JK flip-flop, and this is excitation table for JK flip-flop. How we can get this excitation table from the truth table? Okay, as you can see, this one is present value, and this is the next state Q and T. This is equivalent to T lah. T and T plus 1. Okay, sama saja. Okay, the yellow one. If we want to get the output 0, 0, okay, the input of the JK must be, it is either 0, 0 or 0, 1. Okay, meaning that J, there will be no difference in J, but K is between 0 and 1. That is why J is 0, K is X. It is either 0 and 1. Okay, same goes with pink. The pink yang ini, okay, pink. If we want to get input of 0 and 1, okay, for present state 0 and next state is 1. So the input must be J is equals to 1. Okay, for K it is X. It is either 0 or 1. That is how we get this. Okay, untuk yang hijau pula, okay, input is 1, 0. Okay, 1, 0. 1, 0 and 1, 0. Okay. For the input, J is either 0 or 1. K is must be 1.
Yes. If I can hear you, Yos.
But
Miss, your voice is
sorry?
breaking.
I don't know what happened. What happened to my line? Hello, is it clear now?
Yes, Miss.
I don't know, maybe because kat sini nak hujan ke? Alright. How to get the access table? If not, I want to repeat it again. Sorry, lupa pula nak share. Right. So just now, do you hear? Hello. Is there any? Hello, hi. Is it clear now? Is it clear now? Can anyone?
Yes,
Anyone can?
yeah. Yeah, dah clear
I'm
sikit.
so sorry. I don't know. I'm so sorry. I don't know what happened to my line kat sini. Is it because of the weather nak hujan ke? Aish. Biasanya okay saja. We correct. Continue. We have sikit saja lagi. Kat sini, you guys want me to repeat on this slide? Anyone can answer? Okay, is there anyone can answer? Tak dengar ya? Sekarang dengar tak?
Okey, boleh dengar, boleh dengar.
Boleh dengar.
Saya tak tahu kenapa. Saya tak tahu kenapa line internet saya hari ni. Aduhai. So sorry ya.
Sekarang hujan
Okay.
kot, dekat rumah saya pun dah start hujan dah ni.
Ya, kat mana tu?
Saya dekat Batu Kawan.
Penang ya? Itulah maybe kat sini pun nak hujan kot. Tak apalah, we have I think sikit saja lagi. Okay. Kalau tak dengar lagi please inform so that I can repeat. Okay, just now kita habis dekat sini shift register and excitation table. Is it clear before this yang tadi I explain on the excitation table? You guys can hear? Boleh dengar tak yang tadi? If not, I want to repeat again on the excitation table.
Okey, yang ni okey
Tadi dengar tak?
Lepas ni ya. Yang ni dengar dah.
Okay. Jadi dengar alright. So we go for the next one. Is on the flip-flop excitation table. Okay, the flip-flop excitation tables come from a transition. Okay, and the transition refer to the relationship between the current and next flip-flop output value. Oh, actually, for this slide, I'm using the one that saya dah modified sikit, add on some information. It is slightly different sikit from the one slide in FlexLearn. So you guys can download this slide. I've already uploaded in the Microsoft Teams. Boleh tengok dekat file kat sini ya. Dekat file upload saya dah masukkan, so you guys boleh ambil from here lah. Okay. And for the flip-flop excitation table, from this one. Okay. The potential transition for a flip-flop is from 0 to 0, 0 to 1, 1 to 0, and 1 to 1 transition. 0 to 0 from current value, from t equals to 1, and t, this is t plus 1. Okay, let's say or this one n plus 1. Okay, from 0 to 0, 0 to 1, 1 to 0, and 1 to 1. Okay, the difference is here. Okay, from J, there is no changes, but for K, it is either 0 and 1. Okay, for 0 to 1, also difference kat sini. Okay, this is for this state different here, and same goes for kat sini different here. Okay, by analyzing the excitation table, okay, as an engineer, you guys will be an engineer. One day a designers can ensure that the flip-flop circuits operate as intended and avoid the potential timing hazard or errors. Okay, we don't want that to occur in our system. Okay, next one, this is transition table for JK flip-flop, and this is the excitation table. Okay, how to get the excitation table? Kat sini lah. Okay, we get X because there is difference here. Okay, and here will be X, and here will be X, and here. Betul tak? X, and X here. Why? Because it changed from 0 to 1. Okay, it is either 0 or 1 for the condition here. Alright. Next, we go for state machine. Okay, it is an abstraction model used to give a good representation about the behavior of the system. Okay, each state in the state machine may reflect the current setting or behavior of the system that we want to construct. Okay, it is a mathematical model we use to describe and analyze the behavior of the system that exhibits a finite set and finite sets of the discrete state. Okay, in a state machine, the system behavior is defined in terms of a finite set of states or the condition and the transition between states and action that occur in response to the transition. Okay, the process of moving from one state or one condition to another, okay, we call it as the state transition. Okay, we can represent in state diagram, okay, where every state is represented by an oval shape and arrow. Okay, kita tengok. Okay, this is contoh state machine. Okay, simple traffic light state machine used to model the behavior of a traffic light at a simple intersection. Okay, now we imagine simple traffic light yang dekat kampung-kampung punya. There is no sensor, okay, or no counters. Okay, no setting ya kat sini ya. Okay, we have 3 states. It is light, it is green, yellow and red. Okay. Red meaning go, move, yellow is slow down and red is stop. Okay. We present the 3 states here. Okay. And we use a timer. Okay, kita dah set timer dia berapa. Okay, initially. Okay, this one start with green state, and then if once the timer is expired, okay, and the transition goes to yellow state. Okay, and then here once, let's say we set the timers 60 second ke contohnya lah. And this one once it is expired, we go to the next state. Okay, and dia akan terus repeating lah for this state machine here. Okay. The traffic light system needs to count down to 0 before move to another state. Okay, the counter is a component in the traffic light system. Okay, for example, kita set 60 second for the first one and same goes lah. Okay, this is the system of a simple traffic light. Okay, this is kita setkan the initial counter with the 60 seconds. So the counter dia akan counted down from 60 up until 0. Okay. Okay, for this one, like yellow, just set for 3 seconds. Okay, and then the counter will decrement from 3 to 0, and then it change to the another counter, which is this one is red. Okay, red is for stop. Okay, for 30 second. Okay, and then dia akan pergi to the next previous one lagi to the green state. Okay. Okay, actually for this one we can represent in binary lah. This one. Okay, this is the state diagram of mode 8 counters. Also we call it as a 8-bit binary counter. Okay, this one is the 3 bits is corresponding to the 3 different states. Okay, this state diagram is by using synchronous counter. Okay, note that this is a very simplified example of a traffic light state machine, and remember that in real world traffic light control system can be much more complex. Okay, incorporating sensors, okay, for let's say the sensors, the feedback loops and other features to optimize traffic light flow and the safety. Okay, it is depends on the flow also, the safety. Kita ada put sensors in the traffic light and also the feedback loops lah. Alright, add on many more features. Okay, this is for model of state machine. 2 general models. Okay, we have Mealy and Moore state machine. Okay, the fundamentals between Mealy and Moore machines is that the dependency of the output is on the current state and the input. Okay, for both Mealy and Moore are quite complex machine. Let's see one by one. The Mealy and Moore. First is the Mealy machine. Is a type of finite state machine where the output are determined by both the current state and the input. Okay, the output are associated with the transition between states rather than the states themselves. Okay, this is state feedback. We have state feedback here. Kat sini, why? Because dia akan feedback dekat dalam, same goes dekat input, and this is the logic output. Okay, goes straight to the output. And this is the block diagram of Mealy machine. Okay, the input changes can cause immediate output changes. Okay, because kita ada satu path kat sini. Okay, it is a synchronous condition. Okay, the Mealy machine is not a, we consider it is not a counter. Okay, let's see. Next one is more machine. Okay, this is block diagram of more machine. Okay, the current output of a machine is solely determined by the current state. Okay, kalau kita tengok here, dia ada one path from input direct to the output, meaning that there is a condition. It depends on the output input itself. Okay, now it is only depend on the current state. Okay, the output change synchronous with the state changes. Right, that's the difference between these two. Moore and Mealy machine are generators. Both have no knowledge of a final state because they aren't used to recognize language. Moore and Mealy are finite state deterministic device. Okay, that's the difference between Moore and Mealy machine. As we go for this one is this one is the summary of the Mealy and Moore machine. Okay, you guys boleh baca. I add on this one. Okay, the notes lah, add on in the notes. Okay, we go for the principle of synchronous circuit design. The ultimate goal of synchronous circuit design is to create a circuit that is reliable, efficient and easy to test and debug. Okay, itu adalah dia punya tujuan utama. Okay, now we have flow diagram here. From first is determine the number of flip-flop and counting sequence. Okay, the clock signal is used to synchronize the operation of different parts of the circuit, and then we allow for reliable and predictable behavior. And then we draw for the state transition diagram. Okay, the data flow in the circuit should be carefully managed to avoid error and the glitches. We don't want that to occur. And then we construct table with present state, next state, and the flip-flop excitation table. From tadilah, from the truth table, then we can get the excitation table. And as the circuit designers, you guys should ensure that the data is stable before we use in subsequent operation. So we have to perform logic minimization using K-map, cannot map. Okay, remember we have learned this in digital electronics. Okay, hopefully still ingat. And then we can sketch the circuit. Finally, we can do the testability. Alright, that's the flow of the principle lah. This is the mode 8 counters. Is a type of counter that count mode 8 counter. With this one we design using JK flip-flop. Okay. And this is the transition table. We have present state, next state, and excitation. Okay, mode 8 counters is type of counter that we count from 0 to 7. For example, in binary, it is 3-bit. Okay, 3-bit kan. For 0 to 7, it is from 000 to 111. Okay, because 7, 111 lah. Okay, so 000, we have 000 for present state. And kalau tengok kat sini, we have JA and JK. 1, what's the difference? Q 0, 0, 0, 1 here. And if it is 0, 1, 0, we get 1 here. Okay, for JA lah. Let's say the third is 1, 0, 0. Okay, it is 1 dekat JA. And if it is 1, 1, 0, it is also 1 at the JA. And then we can get the K-map. It is a K-map cannot map. Simplification. Okay, from yang ini tadilah. Okay, from this. This one is JA equals to 1. Okay, this one JA equals to 1 from 1, 2, 3, 4. So JA equals to 1. Kita tengok at C, 0, C and C prime. C prime or C bar lah. C and C bar kat sini. C and C bar, compare semua yang JA equals to 1. That is how to get this. Okay. 0 and 1. 0 and 1. So this one is 0, 0, 0, 1, 1, 1 and 1, 0. Okay, for B and A. Okay, so compare this one. Same goes with the KA, JB, KB, JC and KC. Okay, we have 3 J, K and JA, JB and JC. Alright. Okay, note that this is just one way to design a mode 8 counters using JK flip-flop. Okay, we have other implementations are possible depending on the specific requirements of the circuit. Okay, for the hardware description of HDL coding, this is actually application of HDL coding for digital counter design. Okay, overall for hardware the HDL is salah. Here. Okay, application of HDL coding for digital counter design. HDL is hardware description language. Okay, remember in digital electronics we have VHDL, very high speed hardware description language. Okay, VHDL. Now we have HDL. Overall, the HDL coding is an essential tools for digital counter design. Okay, it enables the designers, okay, you guys as designers or engineers to describe the counter's functionality and behavior. Also to implement the design using hardware devices and to verify and also modify the design when needed. Okay. Okay, for VHDL, very high speed HDL and very low. This is common types of HDL available in the world. Okay, VHDL allows the designers to describe behavior and structure of digital circuits and systems at high level of abstraction. Okay, the language can be used to specify the functionality of a circuit or system as well as the timing, and also can be used to simulate and verify the design before it is implemented in the hardware. Okay, let's see if we go below this one. Okay, this is VHDL actually. VHDL, if you guys remember, I think kita ada satu eksperimen on digital electronics on VHDL. Okay, one of key features of VHDL is its availability to model concurrent processes, which makes it well suited for describing complex digital systems. Okay, for VHDL also supports the use of libraries of pre-designed components, which we can use to speed up the design process and also to reduce the error. You don't want to get error or glitches in the system. Okay. Depending on what of the microprocessor trainer board that we use in the connection. Okay, this is for example we can use the STM32 board. Okay, for the programming we can use Scale Vision program, and let's say we use the trainer board for microprocessors, we use Arduino, then we can use Arduino IDE program. Okay, this one, okay, we have declare port. Okay, port ni we need to declare one by one. Okay, and then this is the condition here. Okay, when this is 0, 0, then we count as 1. Okay, ini we count as 2, this is count as 3, and so on and so forth lah. Okay. Okay, and for the application of HDL coding for digital counter design, okay, we have a state mode diagram of mode 5 ring counters. This is 5 bit. Okay, it is called ring counter because the output of the last flip-flop is connected back to the input of the first flip-flop, forming a circular pattern. Okay, for this HDL can be used to implement the counter design using a variety of hardware devices, such as we have programmable logic device or it is PLD. Okay, also we have the field programmable logic array. Okay, FPGA, or the application specific integrated circuit and so on lah. Okay. For here we have mode 5 ring counter, meaning that we have 5 flip-flop connected in a circular pattern. Okay, 1 flip-flop corresponding for 1 bit. Alright. Okay, this is the coding will look like. Okay, mode 5 ring counter and useful in application where a cycle pattern is required. Okay, such as in shift register design or in controlling the sequence of events in a system. Okay, for example, kat sini lah. Same goes juga, we have to declare port, dia punya bit pin dia. Okay, and the counter. Okay, however, the use of synchronous circuit can be more complex and require more design effort than asynchronous circuit, especially for a high speed or high performance applications. Additionally, the use of clock signal, we can introduce timing constraint and potential timing hazard, such as clock skew and the clock jitter, which must be carefully managed to ensure proper operation of the circuit. Alright, so that's all for the slides in unit 1. Okay. Is there any question? Okay, we have, this is digital circuit design. Okay. I think it is in the middle, the deadline is in middle of June kot. I think dalam 2 weeks, 3 weeks lagi kot. Okay.
11 June.
11 June, yes, okay. So, question 1 rasanya dah boleh jawab. Okay, ring counter and Johnson counter. Ring counter, 5-bit ring counter, D flip-flop. Okay. For question 2, I think it is more on unit 2. You guys can scroll dulu for unit 2 punya tutorial unit, dia punya PowerPoint slide tu. Alright. Full address ni, it is actually covered in digital electronics, dah ada dah sikit hari tu, because previous semester I've teach on digital electronics, so dah ini pun ada dekat dalam in digital electronics juga. Alright, so you guys boleh tengok balik on the notes from digital electronics also. Okay, if you guys have any questions, then boleh WhatsApp saja anytime lah. Okay, is there any question? Ada soalan tak?
No, miss.
Okay, so if there is no question, I think we can end the session. Kalau sekarang tak ada soalan, never mind. Kita boleh end dulu this session. But then later on, if you guys have any question, then you may just boleh WhatsApp saya saja. Alright?
Okay, ma'am.
Alright, so thank you guys for your time. And I'll see you for our next class. Next class kita will be end of June ke? 17 June. Alright. Okay, alright, thank you. Alright, thank you guys. Have a good day. Alright, bye.
Thank you, ma'am.
Alright, welcome.
Thank you, miss.
Alright, welcome.